Okay, so that's a row, that's a column. And if you're having trouble remembering that, right, think about what column means architecturally, right? Like you'll often see, if you look at the Parthenon, you guys know what I'm talking about, right? And you'll talk about these like columns in architecture, right? These are columns, right? And they're vertical, right? That the columns go vertically, they go up and down. Or if you're in front of like a nice house or something, sometimes they'll have columns, or a McMansion, as the case might be, and they'll have columns. So columns are these vertical things, right? And then if you think about rows, like rows of seating in a theater, they go left and right, they're horizontal. So that can help you remember which ones are rows and which ones are columns, right? So rows and columns like that. And then is everyone okay with like, I guess not, but I guess we should go through this. It's kind of hard to show the math of this. So if I'm going to do R2 plus R1 into R2, so I'm going to say, okay, I need to add everything in row 2 to row 1. So I do something like this. Right, and if I add, I get 2, 2, 1, 3, 0, and then I'm going to plug that into row 2. Right? And yeah, that's exactly what A is, right? That was the answer A. Right? So that's how we do row operations. Does that make sense? Everyone's okay? Okay, sweet. Let's maybe do we want another row operation one? Because like there are, this one's a little subjective. Maybe, yeah, it is simple, but it's confusing to explain because it's a little bit weird like that. Okay, let's try this one. It's very similar, but just a little bit different. Okay, so now we're kind of going the opposite direction. Instead of me giving you the row, I'm asking you to tell me which row operation will give me this matrix. And now the real question is, did I make this? Okay, so I'm going to give you about 30 seconds. Okay. And so overwhelmingly, we said D. Absolutely, D is the correct answer. Good job. Again, let me just kind of cover it again quickly for those who maybe didn't understand what we did. So the matrices were, and this is, of course, the problem with linear algebra is that it takes so long to write everything down. Right? This matrix here has what, 12 elements in it? It's so big. And in fact, for this question, the second row doesn't matter at all. -1, -4. And then 1, 2, -2, -3, 2, 4, 1, 1, 0, -5, 5, 5. Okay, so the big hint here is that the only difference between these two matrices is the third row, right? So the third row is different. And the easiest way to figure out what we probably did in order to make the third row the way it is to look at these two numbers, right? And say, okay, in order to make this number become a 0, this 3 become a 0, I'm going to take -3 times the first row and add it to the second row. So I'm going to do -3 times R1, add it to R2, and then, or sorry, R3, and then put that in R3. Okay, now, of course, if we'd written that in another direction, this is the exact same thing. So we could have written it as R3 minus 3R1. That's the same thing. Okay, and let's do that and find out. So if we do that, we'll get 1, 2, -2, -3 plus, oops, sorry, I have to do negative, or I have to do 3 times that, right? So we get -3, -6, 6, 9, 3, 1, -1, -4. So I'll get 0, -5, -5, 5. And I put that into row 3. So that, that gives me B, right? That is exactly what row B is there. Now, another valid thing that you could have done. Actually, can somebody give me another one? So something that isn't one of these two, is there something else I could have done to, let's say, make this 3 equal to 0? Like, even if it doesn't give me exactly B, can someone else give me another operation I could have done to make this happen? Times 2 by 3. So what are you saying? Row 2 times, like, be specific about which. Okay, so Brandon, that's an interesting one. So 1/3 times row 3 minus row 1. Yep, that would absolutely work. 3R2 plus 2R3, or minus, maybe 3R2 minus 2R3. That would absolutely work. That's a great one too. R1 plus R2 minus R3, that would actually work. R1 plus R2 minus R3 into R3, that actually would work, right? Yeah, absolutely. All of those are valid techniques. Yeah, absolutely. All of those would work. This one is a little bit weird. We often don't, like, there's nothing wrong with it, but we often, when we do row operations, only work on 2 rows rather than 3 rows. I mean, there's nothing saying you couldn't, for example, take multiple linear combinations of rows. That's totally fine. Isn't 6 plus -1 equal to 5 not -5? 6 plus, oh, you're right. Yeah, thank you. I got a little jumpy there and put the minus sign when I didn't, but thank you. Okay, now, here's a good time. I actually want to take a step away and show you how would the last one work. So you would go, okay, 1, 2, -2, -3, 2, 4, 1, 1, and then we're going to subtract row 3. Right, so that's the same as just adding all of these. So that would give me 0, 6, 5, -3, 1, 1, 1. Did I do the math there right? Get my numbers. 1, 2. Oh, this is a -2, 2, 4, 1, 1. Okay, there we go. So -2 plus is -1. So is that a 0? And then -3 is 2, 6, something like this. Anyway, something along those lines, right? But it's okay if we do that, write 3 rows in 1 for assignment and test. You could, it's just, usually it's not, you don't want to do it. right? It usually just makes your life a little bit harder. Like generally when you do row reduction, that's not the sort of stuff you want to do. Okay, but here, listen, I want to show you something else. So I want to kind of show you the first step on how we would do this online. Oh, sorry, I sent that just to Curdy. Okay, so everyone go here for a second. Hopefully you can get there. I don't know if some of you are on like VPNs or something. And I'm actually going to share. No, you wouldn't lose marks. It's not the best way of doing things. I mean, it's wrong for this question. Person sent me a private message, but you can add and subtract as many rows as you want without changing the solutions. Like I might have done the arithmetic wrong, but generally you can just add stuff however you want. Okay, so is everyone here? No, I'm saying you are allowed to plug it into your calculators. And in fact, I am going to show you how to plug it into your calculator. Okay, that's what I'm doing right now. Okay, so is everyone at this web page? Now, you don't have to use this. The program that I'm showing you here is called Octave. And if you want to use something else like Symbolab or Wolfram Alpha, you're free to do that if you want. Octave is just far and away the easiest and fastest thing to use. Now, this site here, Octave Online, is, this is for, I'm going to show you, for example, how to row reduce this matrix. Okay, so that you don't have to do all the elementary row operations. I just think this would be a good time to show you. So does everyone remember the matrix that we had? It was, here, I'll just plug it in and then I'll talk to you about how to plug this in. Okay, so this was the matrix that we had, only it was augmented, so it had this little vertical line here. Yeah, no, Brandon, I know you were trying to help, and I appreciate it. Okay, so when we plug a matrix into Octave, now again, if you want, you can just download Octave, but this is a nice thing because you can use it in your browser, so you don't have to install anything. So for that reason, it's nice. But if you want to install it, especially if you're someone with shakier internet, this might be something that you want to do. Now, the way that you plug in a matrix is you plug it in one row at a time, and you separate the one number from the next just by using a space. And then you separate one, you say, I'm going to start a next row by using a semicolon. Okay. So everyone try and do this, plug this matrix in and make sure that you get this matrix out. This was the matrix that we had in the problem. Okay. So I'm going to give you a second or two to see if you can do that. And if you're on your phone, obviously this is going to be tough, but don't worry about it. Yes. Yeah, you can use this during the test. This is precisely why I'm showing you how to do it, so that you can use this during the test. Because everyone, we might, because you have access to a calculator, no, this is not cheating. Because you'll have access to a calculator, we might give you systems that we wouldn't give you in person, in the sense that, if I give you a 5x5 matrix and asked you to row reduce it in person, that's a lot of work. But I'm going to assume you all have a calculator. But it's only fair, if I'm going to assume that I have a calculator, I should probably show you how to use the calculator. Right? Yeah, so I put A equals. You don't have to do that if you don't want to, but if you don't put the A equals, then you can't refer back to it later. Right? So the benefit of writing A equals is that I can do something like 2 times A, right? Because we know how you multiply a matrix by a number is you just multiply every element of that matrix. And I can just now write times 2 times A, and now it all works, right? You got a syntax error. So Brandon, what exactly does your syntax error say? I know, that's what I'm trying to show you. We're doing it together right now. Has an arrow pointing to the -2 in row 1 and points at the first 2. Okay, so exactly, use A equals and then bracket. All right, here, I'm going to do a different matrix. B equals 3, 4, -1, 0, like that, right? And again, hopefully you're seeing the syntax here, right? So put it in a square bracket, has to be in square brackets. You have to put spaces between your numbers and semicolons between your rows. And your rows all have to be the same size, right? Because matrices have to be rectangles. Well, because if I don't use spaces, how do I distinguish between 34 and 3, 4, right? Right, I'll tell you that in a second. That's a great question, Chan. Like, how do we show that we use Octave on a test? You also got the syntax error. Curdy, can you copy and paste what you put in? Like copy and paste this line for me into your code. Yeah, don't worry about the augmentation part. It turns out that's never necessary. That's what we use to keep track of where the equal sign would be. Yeah, so use round brackets, Curdy, use square brackets. It's literally just the equal sign, right? The equal sign on like my keyboard is beside the backspace. If you have a different keyboard than mine, it might be in somewhere else, but most keyboards usually have an equal sign on them. Okay. Anyone else struggling with this? Everyone else has got A? And you notice if you just hit A again, right, the matrix pops back up so you can see it. Okay, cool. You want to know how you put a matrix in reduced row echelon form? That's how.
If only you guys knew how long it takes to do it by hand. Some of them get very, very tedious. So this is like a gift.
So Naga, what do you mean by undo? Like, did you just put A in wrong? If you put it in a wrong number, just do it again. Just say A equals and then fix it. Yeah, it's super awesome, right? And now here's the thing. So let's say I make B another matrix that's the same size. I can do A plus B, stuff like that. Yes, you are allowed to use this during tests and assignments as long as you explain how to do it. And I will show you how you would write this in a test in a second. Okay, so that is how you can do RREF. And what you'll notice here, let me do RREF of A again. So what you'll notice is that we know that secretly there's the line here, right? That there's the augmented matrix has this vertical line here. And what you'll see is that even though in Octave you can't tell it to put the line there, it actually doesn't matter. So I recommend that you try row reducing this by hand. It would just be good practice just to get used to row reducing stuff. And you'll find that you get the exact same answer as Octave does, even though you didn't have like the augmented part here, it doesn't make a difference, okay? And trust me, as far as row reducing goes, this will be the easiest thing that we can do that Octave can do. There will be lots of other really hard stuff that Octave can do for us as well, okay? So that's how you put a matrix into reduced row echelon form. Everyone makes sense? By the way, does everyone know where on the, in Quarkus to get the cheat sheet for Octave? How come Octave gives us 4 decimal places? Because it's not, Octave is numerical, right? So it computes everything in what are called floats. We have to get a little bit into computer science to understand this, but it does tend to give everything in decimals, not as fractions. But here, let me say this.
Tyler, while I do that, just heads up, I'm gonna have to go start the tutorial. So
for sure. Yeah. Okay. See you later, Aziz.
See ya.
Will we always get numbers for this? Yes. Yeah. So it's true in the case where I give you something abstract that has like letters, instead you have to do it by hand, or you have to use Symbolab or Wolfram Alpha. You have to be a little bit careful though if you do those with symbols. Octave does have the ability to do symbolic computation, but it's a little bit trickier. And so I'm not going to show you how to do that. But as far as I'm concerned, if you want to use this for matrices that actually have numbers in them, you can. Now, the course in Quarkus, okay, so if you go to Other, there's something here called the Octave cheat sheet. Okay, so the Octave cheat sheet, if you open this, gives you just a quick little rundown on how to use Octave to do things, okay? And so you don't need to know how to do this. For example, we haven't talked about matrix multiplication yet, but we will, and this tells you how to do matrix multiplication. Again, here's a reminder on how you do RREF. We'll talk about determinants later and eigenvalues and all these things. And the point is that Octave can compute all of these things for you, right? And you are allowed to use any of this in an exam to do your work, okay? So let me just give you an idea, though, of how this would work in a test. So in a test, what you would do is, hold on, let me just go back to my other thing. Yes, stop sharing, use this, okay. Okay, so in a test, what you would do is you would do the following. You would say, you got to your matrix, and your matrix is, let's use the matrix that we had. Eventually you get to this matrix here. You can probably imagine we'll ask you a question that's very similar to the assignment questions, which is to, here's a system, model it, set up the system. 3, 1, -1, -4. And then what I would say is, using Octave to row reduce gives, and then whatever the row reduce matrix was, right? It was -1, 2/5, and 7/5, right? Okay, so that's how you would do it on a test, or you could leave it in decimal format. I converted them to fractions because I usually like working with fractions more, but this is how you would do this in a test, right? You give us the matrix before, and then you write the sentence saying, by Octave, we get, if we are row reducing using Octave gives blah, and the output whatever Octave gave you. Yeah, assignment 2. Yeah, you can do that as well. Okay, now note that in this assignment, we don't actually ask you to row reduce, right? We just ask you for the system. Now, if you want to try it, I'm pretty sure we made it so that the answers actually do work out. So you can plug them into Octave if you want practice and see if it actually gives you the correct answers. If you want to do that, you absolutely can. But this is how you would do this in a test, okay? Does that make sense? Okay, so like I said, don't reject this. It's pretty easy to learn, I think, and we will give you bigger systems because we'll assume that you have a calculator and access to a calculator, right? So there's some sense in which this isn't mandatory. We won't give you like a 50 by 50 matrix and ask you to row reduce it, but we could give you a 5 by 5 or a 6 by 6 sort of thing. It's something you could theoretically row reduce by hand, but you shouldn't, right? I don't know why they didn't teach you how to use this stuff. I mean, listen, there's still value in understanding how to row reduce, because again, I could ask you, and I think a bunch of people are asking this on Piazza, right? Where you get this thing where maybe there's, like if I tell you to row reduce this, Octave's going to have a hell of a time because it's not numbers, right? It's got A and B in it. So you can still do it, and you need to know how to do it. But like, again, a lot of what a computer can do for you, you should understand how it works in general, but there's no point in becoming a master of it because a calculator can do it, right? Could you show us how to row reduce an Octave once again? Sure. So it's like, again, it's in the cheat sheet, but the command is like right here. It's just literally RREFA like that. Right? Once you've saved A to a matrix, you say compute RREFA. Hello, okay, yeah, that's totally fine. Not understanding what steps to carry out. Yeah, that's absolutely fair. So why don't we take, instead of doing more poll questions, let's actually row reduce this by hand. Okay, how about this? So we know what the answer should be, right? Because we computed it here. Let's actually compute this by hand and see if we can get it. And yeah, I think that I had a direct message which asked me to do that anyway. And I'm still not sure how to identify infinite, unique, and no solution. Should I save that for the next day? No, we can talk about that now. So first things first, let's row reduce this matrix by hand. Okay, how about we do that? I think that'll be a good little exercise. And unfortunately, I don't think I chose a matrix which was particularly nice, but whatever. We'll figure it out and we will live. Sorry, just give me a second here. Okay, So the matrix was, I'm actually just going to use Octave to remind me what the matrix was. So the matrix was A equals 1, 2, -2, -3. I'm going to need the higher rows here. 2, 4, 1, 1. And 3, 1, -1, -4. Okay, so let's row reduce this by hand. Now, the Euclidean algorithm says, you're going to look for your first leading one. So this is a good candidate for a leading one because it's already a 1. Once I've identified it, I want to make everything under it 0. Okay, so we want to make these things that I put into squares. We want to make these 0. Right? Because in row echelon form or reduced row echelon form, every number under a leading one has to be equal to 0, right? So once I've identified what I want my leading one to be, I want everything it to be under it to be 0. So first thing, let's make the 2 equal to a 0. So I'm going to do -2 row 1 plus row 2 into row 2. Okay, now everyone, you should, and exactly, yeah, right, which is the same thing that I wrote. So Ahmed, you'll get the same answer, only a negative, which is totally fine, right? So you get exactly the same answer as me, but all of your numbers will be the negatives of mine, and that's totally okay, right? And then 2 R1, and Curdy, yeah, you did the same thing. So it's fine, you guys do it your way, that's totally fine. This is just how I do it. So 0, -2 will give me 0, 4 will give me 5, -2 will give me 7. 3, 1, -1, -4. Okay, and then Ahmed and Curdy, I think you would have gotten -5 and -7. Is that right? Right. Can we write R2 minus 2R1? Absolutely, Sylvia. If you want to do it that way, you absolutely can. And you'll get the exact same answer as me, right? Can you do multiple row operations in the same step, Brandon? Absolutely. And normally I do, actually. But just because I'm trying to show how we would get row echelon form, I'm just going to do it one row at a time. But normally I would also get rid of the 3 in the same step. All right, so that's totally fine. You can definitely do that if you want. I'm just doing it one step at a time. Curdy, -3 R1, exactly, perfect. No problem, Faiza, see you later. -3 R1 plus R3 into R3, right? Or again, you could do, oh, and yeah, you probably mean R3, right, Curdy? Because we're trying to get rid of the 3 now, yeah. Can you tell just by looking at linear system that it has? Not until you get it to at least row echelon form. You need to get it a little bit further. Like there's no way I could look at A and know that it has a unique solution until I get it a little bit further down, at least into REF, if not RREF. Okay, so if I do that, oops, -2, 0, 0, 5, 7. All right, -3, blah. Well, we already did this one. This was the question, actually, right? So this will give me -5, 5, and then 9, so 5, like this. Okay, so far so good. No problem, Victoria. See you later. Okay, so person who direct messaged me are about having trouble figuring out what steps to use. Is everything okay so far? Just let me know. And if anyone, in fact, right, it doesn't need to be a person who direct messaged me. If anyone so far is confused about the steps that I've taken so far, please let me know, scream out something. Everything's okay? Yeah, it absolutely could be. Okay, so you have to take it down to REF or REF. It's your choice. I like to go to RREF always, but it kind of depends on what the question is asking you. So as far as I'm concerned, let's go to RREF. Now, I'm not even close, right? I still have a lot of work to do, but this is kind of what I'm going towards. Okay, hold on. So Quentin, it's my first name dot my last name at utrano.ca. So Tyler, you can find it in the website somewhere. It's in there, tyler.holden at utrano.ca. Person who direct messaged me, it's not guess and check. What I'm trying to do is I'm trying to say, look, I've got a 1 here. And I've got a 3 here. And I want to turn that 3 into a 0. And I have to do that by adding row 1 to row 3 in some way. So I'm not just guessing per se. I'm trying to figure out what the best numbers to use to make that work are. And there are multiple things that I could do, but usually, some multiple of the first row plus some multiple of the second row is the right way to do that, right? For example, 3-2, I need to take it down to REF to identify. Well, okay, hold on. My thing is getting long, so I'll have to look at 3-2 later because I want to finish this before I look at what 3-2 is. How's this? This is not in REF yet. I'm not done. I've only done one step, so we're nowhere near REF. Okay. Okay. So we would need to do a leading row in row 2. So you do 1/5 row 2 to row 2. Okay. So absolutely, Curdy, you could do that. I actually would do 1/5 row 3, row 3. Now, there's nothing say like your technique is totally fine. There's no reason why you wouldn't do it your way. But let me show you why I'd want to do it my way. Because what I want is I don't want this to be the next leading one, because instead, I'm trying to make a staircase sort of thing. I kind of want this to be the next leading one, right? So, and again, you can do it your way because none of your steps are, as long as you every single step always do a legal row operation, then you'll get to RREF and you'll do it fine. But you usually want to avoid doing fractions until you absolutely have to. And one of the things that scares me about dividing row 2 by 5 is that I get 7/5 in the augmented side, and I want to avoid fractions as long as I can. Right? So that's just like, if you're doing it by a computer, you don't care, but if you're doing it by hand, you just want to do whatever you can to avoid fractions. So what I want to do is I actually want to just flip row 2 and row 3. Okay, because the reason is that I want this to be my next leading one. Yeah, you can totally just flip 2 rows, right? Because think about it, like if I give you a system of equations, x plus y equals 7 to x minus 3y equals 4, flipping rows is the equivalent of just doing this, right? And you're like, totally, you can do that, right? You can just move the equation from top to bottom and it's not going to change the answer. So you can move the rows around, right? That's one of the 3 elementary row operations, is you can swap rows around. And now I'm going to make that into a leading one. So I'm going to divide by -5. That's going to be 1, 2, -2, -3, 0, 1, -1, -1, 0, 0, 5, 7, like so. Okay. Yeah, exactly. Right. So don't forget, just being able to switch rows, it's such like an easy thing to do. And now, unfortunately, we do get to this point where I can't avoid a fraction. I mean, there is actually, actually, you guys want to see a cool trick? I can actually avoid a fraction a little bit longer. So the next natural step, I think, for a lot of you would be to say, take row 3 here and divide it by 5, right? That is the next natural step to get your next leading one. Would everyone kind of agree? Like that's the right thing to do? Okay, let me show you something cool. Let's pretend I didn't do this. Okay, I'm going to delete that. Now, if you wrote that in your notes, don't worry about it. Just kind of be like, we're going to try something else and draw a little arrow around it. At this point, I know this is going to be a leading one and that this is going to be a leading one as well. And when I start, if I want to get into reduced row echelon form, what I actually need to do is I'm going to have to start at the bottom and then start killing the zeros above it, right? So what I could do instead here is negative row 3 plus row 2 into row 2. Does everyone see what I did there? So now I've made that a 0 without, and I've pushed it, eventually I'm going to have to go to fractions, right? There's no avoiding it. We know that because we know what RREF looks like. We know it has fractions in it. But by doing this step first, I've actually saved myself a little bit of a headache in adding fractions by making it 0. If there's an easy way to make the number 0 before having to involve any fractions, you should. Now I'm looking at the next number and I'm saying, okay, there's nothing I can do here. Like you might say, well, okay, well, what if we multiplied the top row by 5 and the bottom row by 2 or something to get a -10 and a 10 and to make those things cancel out? You could do that, but it would change the leading one. But okay, so let's say that I wanted to do that. It's a totally legal move, okay? You could do that and it would be a legal move and it would avoid you getting fractions a little bit longer. No, it's again, it's a perfectly reasonable thing. Me personally, at this point, I would start doing fractions, okay? But let's pretend that I wanted to do it the other way, just to delay how long I had until I needed to do fractions, okay? This is legal. I wouldn't necessarily do this, but this is legal. I would do 5 row, or let's say 2 row 3 plus 5 row 1 into row 1. And again, this is weird, right? This is not something that we would normally do because as Curdy pointed out, if I do this, I'm going to change this leading 1 into a 5. And that feels blasphemous because once you have it as a leading 1, why would you change it back to a leading 1? Or why would you get rid of it, right? So let's see what happens. Okay, so I'm going to take 2 times that added to this. This is going to be 5 row 1. So it's going to be 5, 10, 0. And then 14, 14 minus 15, so -1. Is that right? And now I can multiply row 1 by 5 again, or by 1/5. But in fact, why don't I go one step further? And before I divide row 1 by 1/5, let's use this to get rid of this, right? So let's do 2 row 2 plus row 1 into row 1. So that would be 2 times -2 is -4, so -5. Yeah, no, because it's so slick. Look how well it worked out. Wouldn't it have been easier to do 2/5 row 2 plus row 1 after switching row 3 and row 2? What 2/5 row 2 plus R1? You could have done that. The reason why I didn't is because, again, it's going to give me fractions, right? So you're right. There's a sense in which that would have saved me a little bit of time, but it would have led to fractions. And so the only reason I'm kind of taking these extra steps is to avoid the fractions, because let me tell you, I study where our students typically make mistakes when they row reduce. And it's overwhelmingly when you ask students to add fractions. The moment you ask students to add fractions, especially with row reduction, because you're doing like 4 or 5 of them, when you ask students to add fractions, they're going to make a mistake. Why? Because if you ask anyone to add 10 numbers together, they're going to screw up one of them, right? And the moment you make a mistake in your row reduction, everything goes to shit, right? And yeah, you notice that we're basically done. At this point, it's really easy to get the RREF, right? 1/5 row 1, R1 into R1, -1/5 R2 into R2, and 1/5 R3 into R3. Uh, 2/5 and 7/5. Is that the answer that we had before? Boom, it is. This is what we got. Right? Pretty sure? -1, 0.4, 1.4. This is exactly what we got when we plugged RREF into Octave, right? It gave us -1, 0.4, 1.4. You're right. So in RREF, remember, means that every leading one is the only one. It's the only non-zero number in its column, right? See it, Daniel? So now, again, you didn't have to do it this way, okay? The benefit of having done it this way is that I didn't have any fractions until the very end, right? And at this point, the fractions aren't a big deal because I'm not adding or subtracting any fractions, right? I'm just, I had whole numbers until the very end, and then only at the very end did I have to do fractions. And at that point, I didn't care because I'm not doing anything with them anymore. You don't have to do it this way. There isn't a single way to put a matrix into REF or RREF. Okay, there's lots of different ways that you can do it. And as long as you always use legal techniques, that's fine. Okay, so that's something that you can do. If you ever have to do it by hand, you can do a little bit of manipulation, usually just to save yourself a little bit of work. Okay, so does that make sense? Do you see how you can, like, don't dogmatically stick to the algorithm if you can find a clever way to make your life a little bit easier, right? And Dowd, you're absolutely right. We could have done that like -2/5 thing, row 2, but the moment I do -2/5, I've got fractions everywhere, and I'm more likely to make an arithmetic mistake, right? If that makes sense. So that's just kind of like why I would personally prefer to avoid that. Okay, right. So how do you tell when a system has unique solutions or infinite? Now, this is something we'll talk a little bit more when we get to rank, which we will talk about on Thursday, but I'm happy to talk about it now. So remember, when you're looking at the rank of a matrix, what you want to do here, let me just write something down. Okay, so let's say that this is my linear system. This is actually an RREF, right? Does everyone agree? Jeremiah, actually, I'm pretty sure that's the same result I got with my calculator. Okay, so this is an RREF, right? And Jeremiah, I can go back to that in a second. Just let me take care of this. You're right. So this currently has no solution. Ain, how do we know it has no solution?
Because 5 doesn't have like a 1 in it.
Right. Yeah.
Row.
Yeah. So if we think about what this system is, like we write out this equation, you know, it's a 0x1 plus 0x2 plus 0x3 plus, that's a 3, 0x4 plus 0x5 equals 5. And so we're saying that 0 is equal to 5, right? And that's obviously, that can't be possible. And so this doesn't have a system because we have this nonsense equation in it, right? And exactly, Curdy, you said the right thing. So, okay, so now, so this has no solution as it's currently written. Let's say I change this to a 0. Now, what is the rank of the not augmented part? What is the rank of this part? Does anyone remember how to compute the rank? 3, okay, yeah. And how do we compute rank? So for those who are still here and maybe haven't done the videos or the readings that far, how do we compute the rank? What is it? Exactly, it's the number of leading ones in REF and RREF. Perfect, beautiful. So there are 3 leading ones, right? I think we all agree there are 3 leading ones. Now, what you're going to do is you count the number of variables in your system. That's the same thing as the number of columns, right? Each column is a different variable. But how is this REF if there isn't a leading one in the last column? So when you do REF, so first of all, I couldn't reduce this any further, right? Like there's no more leading ones. You can only have at most a leading one for each row, right? So Hala, the next leading one has to be in this row, but because it's a row of all zeros, there can't be another leading one. Does that kind of make sense? Right? Like you put all the rows of zeros at the bottom, and then any non-zero row will have a leading one in it. And so you can only have as many leading ones as there are non-zero rows. We only have 3 non-zero rows, so there can only be 3 leading ones. Okay, isn't the leading, so this is a direct message, isn't the leading one supposed to be in a step pattern? So for row 3, shouldn't be 1 be in the 3rd column? So it doesn't, this is still in a step pattern. And unfortunately, you can't guarantee that they will occur in sequential columns. It is very possible, like in this case that we have here, where the leading ones occur in the 1st, 2nd, and 4th column. And this is actually important. We have to keep track of which columns the leading ones occur in. Okay? So what we're going to do now is we're going to count how many variables this system has. So how many variables does this system have? 5. Okay, how do we know it's 5? Right, it's the number of columns. Perfect, right? So every column is, and Jeremiah, I know you meant rows, right? Because there's only 4 rows. So yeah, you meant columns. So we have 5 columns. Each column is a variable, right? The first column is x1, the second column is x2, and so on and so forth. So we have 5 variables. You have a unique number of solutions. Or you have a unique solution if the number of variables is the same as your rank. Okay? And you have an infinite number of solutions if the number of variables is bigger than your rank. So in this case, do we have a unique number of solutions or do we have infinitely many? Exactly, yeah, 8. So this has infinitely many solutions. And how many parameters? Now here's the next question. How many parameters does our solution set have? Close, not 3, not 4, not 5. Okay, good. But we're going the wrong way. Yes, Jeremiah, exactly. We have 2. So the number, each variable that does not have a leading one is a parameter. Okay, let me show you. Let me actually write this system. So, if we were trying to solve this linear system and I got it to this point, and I'm now actually trying to solve it, what I would do is I'd rewrite this as a system. So I'm going to take it out of its augmented matrix form and write it as a linear system. So we get x1 plus 2x3 plus 7x5 equals 1. Like so. Okay, everyone agrees that that linear system is the one that corresponds to this augmented matrix? All right. Now, let me very quickly remind you of what our Rref is. The process of putting a matrix into row echelon and ultimately reduced row echelon form is to eliminate as many of the variables as we possibly can, right? Think back to even what you were doing in high school when you were solving simple linear systems. You were often trying to eliminate the x's so you could solve for y. And then once you solve for y, you would figure out what x was, right? You were trying to eliminate variables. Our Rref is the simplest linear system, i.e. it is the linear system with the most variables eliminated that has the same solutions as your original system. Okay, it is the linear system which is the easiest to solve, which has the same solutions as your original system does. Now, okay, everyone hopefully is okay. x1, notice that this is the only equation that x1 occurs in, right? This is because of this one. That leading one guarantees that x1, the row that has the leading one in the first column will be the only equation that has an x1. this leading one guarantees that x2, this is the only equation that has x2 in. And this leading one guarantees that this is the only equation with an x4 in it, right? That's what our Rref gave us. Because everything else in the column of a leading one is 0, that tells us that x1 is going to appear in only one equation. x2 appears in only one equation, and x4 only appears in one equation. Does everyone see that? Because everything else is 0, right? The coefficient of x1 is 0 in every other equation. The coefficient of x2 is 0 in every other equation. The coefficient of x4 is 0 in every other equation. So what that means is it's now very easy to solve for these 3 variables, right? I'm just going to move everything over to the other side. All right, and then I'm going to get x2 is 7 minus 4, x5, and then x4, 6 minus 3, x5. There's a fourth equation, but that fourth equation, yeah, exactly. It's 0x1 plus, it's 0 equals 0, right? So it doesn't really add anything. So now I've solved for x1, x2, and x4. And the problem is that when I solved for them, I wasn't able to get x1 is equal to a number, x2 is equal to a number, x3 or x4 is equal to a number. That would be if I had unique solution, right? I would just get x1 is a number, not some expression in x3 and x5. So my answers depend exactly. So we are going to assume that x3 is s and x5 equals t are our parameters, right? They're our variables. And that's why it has infinitely solutions, right? Because x3 and x5 can be anything. If I let, say, x3 be 7, just randomly, and x5 be negative pi, then I could plug this in and compute what x1, x2, and x4 are, and that would give me my answer. So as Agam says, what we're going to do is we don't want to call them x3 and x5. This part might feel a little bit pedantic, but we just want to give them different names to separate them from the fact that x3 is a variable and s is a parameter. Okay, so what we usually do here is we say, let x3 be s and x5 be t like that. Notice that x3 and x5 are exactly the things that don't have leading ones, right? Because we solved for our leading ones, x1, x2, and x4. So the columns that didn't have leading ones all end up on the other side of the equal sign when we solve for them, and so end up becoming parameters, right? This is why the number of parameters is the number of variables minus the rank, right? So in our case, number of variables was 5, rank was 3. So when I subtract those, I get 2 parameters. But it kind of comes out naturally anyway if you actually solve the system. But this understanding the relationship between rank and the number of variables gives you the ability to figure out how many parameters it has and how many solutions it has just by looking at the Rref and not having to rewrite everything as a linear system, okay? So if we now take this, all I'm going to do now is the rank is the number of leading ones. Absolutely. That's exactly what it is. And now I'm going to rewrite this as 1 minus 2s minus 7t. 7 minus 4t. Now at this point, I'm going to actually include the parameters as well, just because I'm trying to write down all the solutions now. Right? We said x3 was equal to s. So that's why when I included, I put the s here. Like so. Okay, so what this says is if you give me any values of s and t, then I will plug them into this and I can figure out what x1 is, what x2 is, what x3 is, what x4 is, and what x5 is, and that will be a solution. And any value of s and t that you give me will be a solution, right? So that's why we have a 2-parameter solution set. Does that make sense? okay? And then if we want to write this as a linear combination of vectors, we would get this. Is the 5 purposely in column 2, or it doesn't matter? Which 5? For x3, bottom left. Is, oh, that's an S. Sorry, that's an S. Right, because it's this parameter. Does everyone see how I did this last thing? Okay. And I don't think this week I asked you to talk about particular and homogeneous solutions. That I don't think that was this week, right? I don't remember because it was before the reading week. Does anyone remember whether we were talking about, oh, it was the last vid? Okay. This is the particular solution. This is the homogeneous solution. All right, so for those of you who have looked ahead and done the homogeneous, read and looked at the homogeneous video, when I say every solution is a linear combination of the particular and the homogeneous solutions, this is what I mean. No problem, Rowan. See you later. Okay, so there was a lot of stuff going on there. I just want to make sure everyone's okay. So we row reduced a matrix. I guess there are a couple of things that I need to ask. One is, Siahala, is everyone okay with the steps to row reduce? Well, this actually is a non-homogeneous system, right? Because remember, homogeneous means that everything in the to the right of the vertical bar in the augmented matrix is 0. So this is actually a non-homogeneous system. But what the homogeneous part does is if I made that 1, 7, 6, 0, if I made those all zeros, then XH here would be the solution to that system, right? Okay, so that's what the X sub H part means, that it's the homogeneous solution, is that if I actually took out the 1, 7, 6, 0 and instead just made them all zeros, then this part would be the solution to that. Okay, so I understand what you did for the last part, but how is this infinite and what did you do for the second last part? Okay, so it's infinite because any value of S and T is a solution, right? Try it. Choose S is equal to 1 and T is equal to 0 and compute what X1, X2, X3, X4, and X5 is and check that, this linear system is satisfied. Does that make sense? And that works for any value of S and T. No matter what value of S and T you give me, these values for X1, X2, X3, X4, and X5 will satisfy this linear system. And so there are infinitely many choices that you could choose for S or T, right? Because you don't even have to choose whole numbers. You could choose like fractions or weird numbers like pi or pi over square root 2 or things like that, right? So that's why there's infinitely many solutions, because any value of S or T will give you a solution. Okay. All right, let's see. You want to do something similar to 2B for assignment 3? I think we already have. I think I might have just done something similar. Sake of notation like this. Well, did you do 2.1? Curdy, did you manage to successfully get part? No, it should be B. So actually, if you go and I fixed this a while ago, but you probably downloaded it before I fixed it. So you were saying F, and I think that a while ago this was F here, right? Yeah, it's B. Yeah, I fixed this a long time ago, but if you downloaded it right away, you wouldn't have seen the fix. I should have announced it. That's my bad. Yeah. So basically part 2 is part 1, but instead of giving you particular numbers for the vectors, they are now kind of abstract, but otherwise it's the exact same question, right? So question 2, part 2 is the exact same as question 2, part 1, only now these vectors are abstract. You know, very similar to when we were doing financial math. You remember how we gave you actual numbers in the beginning and then we slowly started to make them a little bit more abstract. Same thing here. Part 1, actual numbers. Part 2, exactly the same thing, but now get rid of the numbers. So that's what I'm trying to do there is I'm trying to scaffold you into the next question. And exactly, there's no computation. I don't want you to do any row reduction. You could though now, right? Just plug it into, like I said, plug it into Octave and just, you know, to get a little bit of practice working with Octave. I don't think I made the answers for part 2 work out nicely. So you might get some hideous numbers, but you know, you could now just plug it into Octave, but it's not required for the assignment. Yeah, you don't have to do it. Does V sub I M mean infinite? No. So what it means is that, so in part 1, we were working in R3. So in that case, M would be equal to 3. So what I'm saying in that case is, you would have vectors like V1 is V11, V12, V13. The second vector is V21, V22, V23. The third vector is V31, V32, V33, right? So what the bottom number here is doing is keeping track of which vector did you belong to. And then the upstairs number is keeping track of, oh, I'm the third component, or I'm the second component, or I'm the first component, right? So the bottom number is keeping track of which vector you belong to, and the top number is keeping track of which component of that vector you're in. Okay, so it's not like an exponent, right? It's just keeping track of where you are in, like which element you are, because we need 2 indices, one to keep track of the vector and one to keep track of which element of the vector you are. Because yeah, I'm not ready to teach you about infinite dimensional linear algebra. Yeah, exactly. Write it as an augmented matrix. Exactly like you did in part 1. Exactly like you did, instead of having a vector 1, 4, -2, you have this, right? So in part 1, this would have been 1, 4, -2. And now it's V11, V12, V13. But you're going to do exactly the same thing. It's not more vague, it's more abstract, I think is what you mean, right? Because it's the question is the same as part 1, which I think you understand. So it's not that hopefully it's not that the question is not clear about what it wants, it's that it's less tangible, right? Because there's so many more variables. There's I's and M's and B's and V's. So it is more abstract, but the reason why we teach abstractness is if you're comfortable with abstractness, it's very easy to usually translate that into concreteness. If you only work with concrete stuff, it's very hard to see the bigger picture. So abstractness actually gives you the benefit of being able to deepen your understanding of a question. So that's why we do make you do some abstractness. You might be like, well, why would I ever do this, right? Like, who cares about this in real life? Well, the answer is, again, abstraction actually helps with comprehension. And exactly, the B sub m's as well. So the B sub m is like, I started opening the notes because Agnes wants asked me to do 3.5, but let me just pull up the assignment again. Yeah, the B is the same as, it is playing the exact same role as the B is in part 1, right? So instead of 3, -12, -6, you have like B1, B2, B3, right? Exactly the same. Why is that? Yeah, it should probably be in there. If B showed up in your augmented matrix for part 1, it should show up in your augmented matrix for part 2. Okay, let me read 3-5. Consider a closed economic system. For example, column 1 describes the total economic output of the telecommunications industry. How can I type the long close bracket? The long close bracket. I'm just trying to figure out what you mean by that, Yidong. I could probably tell you, but I'm just trying to, not certain what you mean. Yeah, that will, except that would be the open bracket, but yeah, I think maybe that's what Yidong means. Yeah, so, I mean, again, it's going to depend on your keyboard. For me, for example, it's beside the backslash, but yours might be different. So you might have to figure out where it is. Like for me, it's beside the P button. Mm-hmm. Yeah, and like a standard American keyboard, that's where it'll be, right? Like, let me see if I can just hold this up. So for me, oh, how is this going to work? Where the hell is the P? Here they are.
Oh no, I think they meant because like there in the bracket there could be like 5 equations, 3 equations, and they meant that like the size of the bracket.
The size of the bracket. Well, I mean, so, and for Octave, right? All right, hold on. Let's send this somewhere else. So it shouldn't matter how many equations you have, right? Like 6, 7, 8, 9, 10. Right? Like, am I misunderstanding what the goal is? Like implicitly, you know, the brackets are kind of on either side of this matrix, right? Like we understand that they're there, but the way that we type them in is using these. So Yidong, did I misunderstand what you're asking? Or does this clear it up, or? So it's good? Is everything okay? I'm gonna hope that things are good. But if they're not, you know, just let me know. I'm happy to go back to that. Okay, so Leontius economic equilibrium states that there exist equilibrium prices that can be assigned to the total outputs of the various sectors in such a way that the income of each sector exactly balances the expenses. Prices of the total annual output of the telecommunications hydro services the system equation describes Leontius equilibrium. Okay. So let's see. Purchased by distribution of outputs. So column 1 is the output. Right. Okay. So we've got this table. So this is 3-5. And we've got this table here. THS, THS, 0.1, 0.2, 0.7, 0.6, 0, 0.4, 0.4, 0.4, 0.2. Then we've got the price of each. And so the total states there exist equilibrium prices such that each that can be assigned to the total outputs of the various sectors, so in such a way that the income of each sector exactly balances the expenses. All right, I gotta try to remember what the hell this is saying. Right. Okay, so here, let's just write this out and see if this makes sense. So I claim that each of these things are the costs. To each, what did we call them? Service, system? Right? Because if I write this out, this says T spent 0.1 times the price plus the price of whatever H was, hydro. 0. Let me write this a little bit cleaner. 0.1 times the price of the telecommunications, 0.6 times the price of hydro, plus 0.4 times the price of whatever the heck S is. This is 3-5. Right? Oh, am I not sharing my screen? Oh, I'm not sharing my screen. Jeez, sorry. I'm being dumb. And then of course I didn't look up soon enough to. Yeah, okay. Okay, so this is 3-5. So in 3-5, let me just kind of like quickly reintroduce things. So in 3-5, we have this table here. Okay, so if you pull this up from the notes, it gives you this table. And the each column tells you the total economic output of each industry, right? So this is the economic output. Of the telecommunications industry, okay? And so the way that we read this is that 0.1, or rather that 0.2 or 20% of the total economic output is purchased by the hydro company, right? That's what this means. And that 70% of it is purchased by whatever S is, the services economy, whatever that is. And then 10% is retained as operating costs. Okay, so that's how we read this table. And we're told that the price of the telecommunications services is PT, the price of the hydroelectric service is PH, and the price of the service economy is P sub S. Okay. So what I want to do then is set up a linear system which computes each of their costs. So what I'm going to do is I'm just going to take a linear combination of the price times the economic output, right? And so if I figure out what this is saying, this should be the total cost for T, right? It spends 10% on operational costs. It spends 0.6 times pH purchasing hydro, right? So it purchases 60% of the hydro's economic output at a price P sub H, and it purchases 40% of the service output at a price P sub S. So this is the total cost to the telecommunications industry, right? And then, and so on and so forth for H and S. And then the economic equilibrium states that there exist prices that can be assigned to the total outputs of the various sectors in such a way that the income of each sector exactly balances the expenses. So what I think that means is that we want this to be equal to 1 times P of T. Right? So the income is 100% of your economic production times your price, right? That's your revenue. So this is your cost slash expenses. This is your income slash revenue. Having trouble spelling. Right? Does that make sense? And so you would do that with each of these things. Why is it 1? It's 1 times. So it's like 1.0 times PT. Because remember, so PT is the price that the telecommunications industry charges. And so their total income is 100% of their economic output multiplied by the price that they sell at it, right? That's their income. So just like this is, we're taking 60% of the production of hydro and multiplying it by the price of hydro gives me how much we spend on hydro, right? It's the cost of hydro times how much of it we buy, which is 60%. Our income is 100% of our output times the price of our output. Does that make sense? Okay, and so you can see that this will give me that 0 is equal to 0.9 PT plus negative 0.9 PT plus 0.6 pH plus 0.4 PS. And so you do that with the other equations as well, and you should get 0.2 PT minus 1 pH plus 0.4 PS equals 0.7 PT plus 0.4 pH minus 0.8 PS. Right? And then you just solve this linear system. Right, so that's part A, and then part B is solve it. So to solve it, you just throw that into Octave. Or practice, right? Practice row reducing by hand. Why is it -1? Like, why is it -1 here? Is that the question? Yeah, okay. So as a system, right, we would say this is 0 pH. So that's from this. But then that also has to be equal to 1 times pH, right? Because again, that's the income. And so when I make it a homogeneous system to put the pH on the other side, I get -1. Is it wrong to put your linear system of equations in brackets? Yeah, you shouldn't do it. If you wanted to do it like this is fine, right? Because now this is an equality of vectors, that's okay. But you don't want to put it inside, you don't want to write like x equals 7, 3 equals y or something like that in brackets. That's generally, that's not good for it. You don't want to do that. Yeah. Okay, so direct messenger, that's, sorry, it was your that's why the -1 makes sense. That's okay. Right, and it was the same thing why this is 0.8. It's actually 0.2 PS here, but then it should be 1 times PS on this side, but then when you subtract it, you get -0.8. All right, so a little bit of economics for you. I don't know if you all do that, Leontief's economic equilibrium. Yeah, perfect, no problem. I don't know if you guys would do this in economics, but this is an economics application. Do we have Zoom classes in the month of December, or is there a specific last date? Yeah, the last date is like December 6th or something. If you go to the list of important dates for UTM, it'll say when the last day of classes is. I don't exactly remember when it is. For us, let me see. Actually, I think I have it in my calendar. Last day of classes is December 7th for us. However, we probably won't. So December 7th is a Tuesday, right? Because we started on a stupid Wednesday. So our last day of classes is a Tuesday. But we won't do anything in that last week. So for us, really the last day of classes is December 3rd. And then December 7th will be like, you can come if you want. Last year, I think we all just played Among Us like as a class or something like that. Yeah. Yeah, we were doing stuff like I actually went over to TJ's lecture because TJ and I actually taught at the same time. So I moved all of my students into his class and then we were playing games and stuff. So that's what we did there. But if you want to skip it, obviously you can't because there won't be any content there. Okay, everyone, but I think that takes us, we're a little bit past 7 now, but hopefully, does anyone have any last minute, maybe quick questions that I can answer? Otherwise, we'll call it a night. No problem. Thanks, everyone. All right. Work hard, study hard, and I'll see you on Thursday evening. Okay. See you later.